Okay, any question about the previous session? In the previous two sessions, we start the normalizing full models, where we see that the core idea was to use a invertible transformation to change a simple or base distribution in the latent part into a more complex distribution, and because of the invertibility, you can easily calculate the distribution in the target domain, or in the what you observe, the domain that you observe. We call it X. This was a very simple example. We see how we can calculate the distribution in the target space, and now we can use a parameterized, let's say, the transformation, and try to optimize the parameter of that transformation such that the target distribution is as similar as possible to your data distribution via distance metric, for example, KL divergence, which is equivalent to maximum likelihood estimation, maximum likelihood of data, giving maximum likelihood to the data coming from data distribution by your model. Okay, this was our notation, and we see how we can combine several invertible transformation like F1, F2 till Fl, and we can combine them together to have a more complex invertible transformation, and we see how we can calculate the Jacobian, because we need the Jacobian for normalizing the distribution. So the most important part was that this Jacobian must be calculated easily, and it should not be complex in terms of resources needed to calculate. Okay, and this was the generation way. This is the density estimation, and also we see the learning part. Again, for the learning, we need to maximize the likelihood of data coming from data distribution under your model. How probable your model assume the data coming from the true data distribution. If you maximize it in terms of the parameters of your transformation, it means that you are training the model. And we see that how we can calculate the likelihood of data. This is the way we can calculate the likelihood of data. And finally, this is the term that we should maximize to have the maximum likelihood. This is the problem in terms of inverse transformation, G, and this is the loss in terms of forward transformation, F. And we see the first model that designed those transformation, and it was NICE, Nonlinear Independent Component Estimation. We see that NICE divided your data into two parts. It selects a random integer between greater or equal than 1 and less than your dimension, and then the first part is exactly copied. The second part is the second part in your observed data is the second part in your base data, plus the output of this M function. We can see better in the figure. I updated these figures. You can have better visualization of the process of additive coupling layer. What happened first in the forward transformation, it copied the first part of the base data into your observed data. This part can be easily inversed because it is identity, so you have another identity transformation, and you can generate the Z given x. Then for the second part, first it calculates a vector y. This vector y is of the same dimension as your second part, and it is the output of this arbitrary transformation. There is no limitation for this transformation. As we see before, it can be invertible or not. It can be both invertible or not invertible. So you generate this y using the first part and add it to the second part, and consequently you have the second part in your observed data. How we can inverse this procedure? Because you have the first part exactly copied in the first part of the observed data, you can easily again generate y using this first part of your observed data, and then if you subtract it from the second part here, you can generate z. So it is invertible and can be easily used as one layer in a model based on normalizing flow. This is the forward transformation, this is the reverse transformation, and we see that the Jacobian is very easily independent of the model parameters, or in other words, this is volume preserving, so the Jacobian terms in your loss are independent of the parameters, so you can easily omit them from the loss function, and you have a very simple loss function. Okay. We see that the transformation is volume preserving, and this is very suitable in terms of computation cost. And also in NIS we have some rescaling layers in addition to the additive coupling layers. In the rescaling layer, you just change the scale of your input. Each input is multiplied by a non-zero constant, a non-zero parameter, and this parameter is the parameter of your transformation. Again, so this is element-wise. Each element is multiplied by a corresponding parameter and then generate the observed data, and easily you can invert this process by dividing the observed data by that layer parameter. So it can be easily done. So you have this element-wise operations, and you have this forward transformation and this reverse transformation. The Jacobian is also really simple. It is a product of the parameters, and you know that we have a logarithm of this term, so it can be easily converted into the summation of the logarithms. This was the result of NIS for MNIS data set. This is the for MNIS data set. This is for phase data set, for SVHN and CFAR and CFAR 10, I think, yeah. Then we were talking about an application, application of NIS for image Inpainting. Assume that you are given an image, and this sample is, we call it X, and it has an observed part and also a hidden part, which is corrupted. And we want to estimate the corrupted part. What is our assumption here? Our assumption is that we have a parametric transformation, invertible parametric transformation. So for each point, for each data point, I can easily calculate this likelihood. How I can calculate? I first calculate the corresponding z, and using the probability of z in the base distribution times the absolute value of the determinant of the Jacobian of, for example, reverse transformation. This is the normalizing flow and how it calculates the data likelihood. So every image, for every x, I can calculate the probability and assign a number to that x. But here the problem is different. The x you observed, the x is not completely observed. A part of x is observed, we call it xo, and another part is corrupted, or to some, and we can assume that it is masked. It is not corrupted. You do not have access to it. We want to find an estimate to the corrupted part. So what can we do? We know that we do not have access to this conditional distribution. We do not have access. We have just access to this distribution over the complete data. So you cannot calculate this term directly. But based on the Bayes rule, you can rewrite this conditional distribution as this fraction, this ratio. The joint over the probability of what we observed. Okay, the denominator is accessible. How? It is the probability of a complete image. So you have it via your normalizing flow model. Okay? Do you agree we have the denominator and it is accessible via your model? Any question? But the denominator is also not accessible because it's the probability of just a part of image. So what happened to the denominator? How we can deal with that part? Pay attention that the maximization is with respect to the hidden or corrupted parts. Okay? So for each of these xh, this denominator is a fixed number. It's independent of xh. It's the probability of what you observed. So it is independent of what happened on the corrupted part. So you can easily omit it because it does not play any role in your maximization. Do you agree? So we can, instead of maximizing this ratio, we can maximize just the denominator. Yes.
I have a question with the previous slide.
Yeah.
Did we go over how
This?
how nice does sampling? Did we go over the procedure which produced these results?
You mean the procedure of sampling from this? We go.
So we haven't touched that yet.
What?
We haven't touched that yet.
Yeah. Especially in the next part that we talk about the autoregressive part, you can see that easily how we can sample from them. Yeah. Okay, but the general case of sampling we have here. Sorry for the flying. Yeah, here. This is the general case of sampling from a flow model. In the flow model, you have a latent or Bayes distribution can be easily sampled, for example, the Gaussian. Then you pass it through your distribution. Any sample generated, for example, in the Gaussian, passed through the distribution is expected to be as typical and similar to what you have in your data set, right? Because you train this model, you update this theta such that this distribution is as near as possible to a true data distribution, you know? So the sampling is very simple, but it may be tricky in some cases. But in the case of what we have in the NIS, it can be easily sample generated using this distribution because we know that this F is composition of several coupling layers, additive coupling layers, and rescaling layer. It means that you have several rescaling and coupling layers. They are all trained. So you sample from your Gaussian and pass it through each of these layers, and in the output you have one of those images. Is it clear? Okay. Let's talk about the inpainting and how we can inpaint the image. So you agree that we have this maximization? So what happened here? Instead of loss function, which is a dependent, which is where the parameters of the maximization is your model parameters, here you want to design the input. Which input best suited this model, hidden part or masked part? Okay? It means that, for example, I am in MNIST, okay? And this part is missed. This part is visible, This part is missed, is blocked. So previously you trained a model over MNIST. You have a trained model over MNIST. What can that model tell you? That model can tell you, for example, this is a probable, for example, is this a probable, this is an image. Is this a probable MNIST image or not? That model can tell you. Why? Because it is trained over MNIST, it can understand the architecture, the way that the digits are written. So with a high probability, it gives low probability to this image. But how if I update it, for example, in something else? It gives again a low probability. But if I go near something which is understandable in terms of an MNIST digit, it gives you a high probability. But you do not want to, by search, find the best option. How? Instead, you assume that this part is the variable of your optimization problem. You have an optimization problem where the hidden part or the corrupted part is your optimization variable. It means that you want to change it so that you have the best fit, you have the best field image. Okay? So you start this maximization, you have this optimization problem, and you can easily check that, how you can take the gradient of this joint distribution with respect to the hidden part. Pay attention that the observed part is fixed. You do not do anything with that because it is your information, and based on that information you want to fill the missing part. You change these parts such that the best fit your model is attained, and that's your filling. So pay attention that the model parameters are fixed. It means that you do not need to optimize theta. And we should maximize the joint with respect to the hidden part or the part which is missed. So I can use this gradient descent. Why I use plus here? Maybe I need a step function, step parameters also here, gradient step. Why I add a plus sign here? Because I am maximizing this joint over what I have not access to or what is hidden. If I repeat this procedure for several times, finally I have these results. Assume that this is the original samples. What happened in the middle? I apply some corruption to these images. For example, for the first one, the upper half is missed. For the second, the lower half is missed. For the next one, some noises is added. You can see the left and the right part are missed. The center part is missed. And in these two extreme cases, you cannot understand what is inside the image. Okay. Now, put this part aside and focus on this part. This is your input. But you know which pixels are observed. It means that even for this image, you have access to the fact that which of the pixels here are valid. This is an important information. But here we assume that it is given, okay? Now we start maximizing the joint over the hidden parts. We know that each of the pixels which is not observed is a part of the hidden segment of the image. So I start maximizing with respect to those pixels, and this is the final result. Pay attention. For example, for this image, the lower part is exactly the lower part here because we do not change it, because it is what you have. This is your information. But the upper part is filled by your model. Why? Because the model understands that when the lower half is something like this, the model understands that when the lower part is something like this, one of the most probable filling for the upper part, for example, is this one. So it designed the upper part by maximizing the joint. Is it clear? So all of them are the result of filling the missing pixels in the middle column, and the results are here. And you can see that even for these highly corrupted rows, the last two rows, for example, these images, which are the original images, are almost recovered, except for the last part, which is some of them are missed. But again, you can see that the filling is somehow that you can understand the image in each of these samples. Any question about this example and how we can fill the missing parts? Okay, any model that give access of, for example, maximizing with respect to a part of the input can be used for this type of inpainting, because you need to maximize the joint over a corrupted part. The information of the corruption here are also written here. The last two columns are 75% random and 9% random corruption. It means that 9% of the pixels in the last row are corrupted. Just 10% are observed, and those observed are given to you. You know that which pixels are valid and observed. Any question? Okay, next we go to another normalizing flow model. You see that the coupling, the NIS uses additive coupling and rescaling to generate the your transformation. Here, the authors propose to use a coupling layer instead of additive coupling layer, and you see that how it works. Again, you select an integer d greater or equal to 1 and less than uppercase d. The first part is exactly copied, but then the next part, the second part, is somehow scaled simultaneously. Previously, the second part was just added with the transformation of the first part. It means that we do not have this scaling, but here we merge them together. It means that you simultaneously rescale and also add something to your second part. Where these two, S theta and T theta, can be any neural network architecture. There is no limitation over them, such as invertibility. So, what is the reverse inverse transformation? The inverse transformation, again, the first part is copied. For the second part, first you subtract this added part, and then you instead of multiplying with the s of theta, you multiply with the exponent of minus s of theta. We know that the exponent of minus s of theta can cancel this term. But we know that for the inverse part, we need just to use x values. But we have z here, and this can be solved by the fact that the first part is exactly copied. So you can replace z of 1 to d with x of 1 to d here. So you have one transformation, which is just a function of what you observe, and this is your inverse transformation.
Is that circled on Harumaf product?
Oh, no, it means that element-wise product.
Okay.
Oh, sorry. This, I think we have in the foundation slide, that this is the element-wise product. Element by element product. It means that the output of this network, this neural network, is a vector of the dimension of the second part, and it can be multiplied in an element-wise manner. Yes?
Why do these architectures do such a random D, and then series of different layers? Doesn't that mean like the elements at the end of the feature vector are more transformed in the beginning.
Oh no, that's not the case. Sometimes there are. You can refer to the papers for the more detail, but they have some permutation layers also. There are some layers in between that they just permute the dimensions, so that the first part and the second are not. No, there is no difference. Yeah, they permute them, so that you have access to different alignment of the data. Yeah. Even for this paper, there are also lots of different ideas in this paper that we do not consider here because we do not have time. But there are some batch normalization layers here introduced for the case of invertibility, and you can check them in the paper that is cited above. But this is the main idea where the invertibility comes, so we talk about that. Yeah, but there are lots of different ideas to work them better. Okay, this is the way that they transform the data. Any question? So let's see the visualization of this coupling layer. The first part is exactly copied. The first one is exactly copied into what you observe. So the inverse is exactly the identity again. So you can easily reconstruct the first part. For the second part first, you pass the first part into a network S of theta, so it is a parameterized transformation, and it is arbitrary. It can be any transformation, there is no limitation. Then the output is passed through an exponential function. This is again an element for its exponential. And then you have a vector v here. This vector is exactly the same dimension as your second part. It means that the dimension is d uppercase D minus lowercase d. So it can be multiplied by your data, and then again a similar vector with the same dimension is added to the result, and then you generate the second part. This is the forward transformation, the complete forward transformation. So for the inverse transformation of the second part, what happened? I again generate W and V using the first part, because the first part is exactly copied. I use the first part of what I observed, which is exactly the same as the base data, to generate W and V. And again, W is minus the inverse transformation of this plus, and I have the U that I have here is now here, and then I divide the U by V, which generate the Z for me. So this is the inverse transformation. Clear? Okay. So what is the Jacobian? What do you think? What happened in the Jacobian? Previously, for the additive coupling layer, what was the Jacobian? The Jacobian was equal. The Jacobian was such that the determinant was 1, independent of the model parameters. What do you think about this type? Because you have some scaling part, you expect some different formulation for the Jacobian, and it is what happened in the practice. So the first part, we have 4 blocks for the Jacobian. The first block is the derivative of the first block with respect to the first block of the input, which is identity y, because you exactly copied them. The second part is 0, because the first part is the formulation of the first part, as you can see here. This part is independent of this part, so this block is completely 0, as you can see there. This block is complex. This block is complex, so we put it again here, and it is not important for us. The last part is again the diagonal. Why? Because how this Z affect the second part. The second part of Z affect the second part of X is just via this is an element-wise manner. It means that ZD minus D plus 1 just affect X D plus 1. So this part, this block is diagonal, and all other elements of the diagonal elements are 0. And for the diagonal element, you have just an scaling, because the addition of that part is not affect the gradient. So you just have the scales on the main diagonal. So this is the complete Jacobian matrix, and we know that the resulting block is lower triangular, because the upper triangular part is completely 0. So the determinant is the product of the diagonal elements, and the first part of these elements are all 1, so they not contribute to the Jacobian, to the determinant. So just we have the multiplication of the diagonal elements in this block, which can be easily written as this formulation. We have the exponent, the multiplication of the exponent, so we have the exponent of this summation. And as you see before, here we have 1 for the case of additive coupling layers, but here we have the exponent of the summation of these terms, which originates from this multiplication. So this term is added to your loss function. Any question? The likelihood becomes more complicated in comparison to NIS, because in NIS it was 1 and you can easily omit it from the optimization problem, but here you have something which is dependent to your model parameter, to your transformation parameters. Another important important point is that it is not volume preserving. Why? Because if the result is Jacobian equal to 1, it means that your normalizing factor was 1, so the volume was preserved. But here the volume is changed, so the normalizing factor is not 1 anymore. So it is called real NVP. What does it mean? Real, it stands for the real world data. We know that all the flow models are for real data. It means that they cannot be applied to a discrete data. And the NVP stands for non-volume preserving, because you have the determinant other than 1 here. So the volume is changed. Any question? Okay. Also, there are some other ideas in real NVP paper, and you can check them. They are not very hard to understand. Based on the idea of flow models, you can easily understand them. For example, they combine several coupling layers. It is not one coupling layer. There are several coupling layers. They also used a type of mask convolution for partitioning. They are also designed to preserve the flow model's property. They use multi-scale architecture and batch normalization, and optimize all of these layers so that they can be viewed as a normalizing flow model. And these are the results which are really interesting in comparison to previous ones. As you can see, the left column are the dataset examples, and the right column are the generated example. Maybe in this image you cannot see them very well, but here you can see some valid face images to some extent, valid images. That is really interesting in the time that the paper was published. And this is just the result of normalizing flow with using these ideas. And how they sample it? Again, they sample the base, pass it through the transformation, and generate the images. And this is the results for ImageNet of this size, 32 by 32, and this is the result for ImageNet of 64 by 64 dimension. Again, the left column is the original samples, dataset samples, and the right column is the generated samples. And also they check another idea, which is the interpolation of the variable. Let's talk about this idea a bit more. We know that if assume that I have two images. I have image x1, and we know that corresponding to this x1, if I have a flow model, I have a z1. And the correspondence is 1-to-1 because the transformations are invertible. x1, x2 has a corresponding z2, x3 has a corresponding z3, and x4 has a corresponding z4. Okay. We know that if I interpolate between these two images, assume that I want to generate a new image by using this transformation. What do you think about this image? This is an image because I add two images one by one and divide them by 2. So the value of the pixels is also valid. There is no contradiction with the pixel value. What happened in the resulting image? What do you see in the image? What is your idea? I have something in between. It means that you can observe both of the image in the resulting image, but it is not a valid image. For example, one image is an image of a bedroom, another is an image of a natural scene. If you add them together, you have a bedroom inside a natural scene, which is not meaningful. But assume that instead of interpolating the data itself, I interpolate the latent space. It means that I have to, let me see, just talk about how we interpolate them. Assume that I put Z1, Z3, Z2, and Z4. This is the corresponding Z for the X images, okay? I put them in this grid, and using this formulation, you see this formulation is a type of interpolation. It means that I can fill these blank boxes using this formulation. So each blank box is a function of these Z1, Z2, and Z3 and Z4 based on the value of phi and phi prime. Okay. So I can fill all of them. What happened if I can fill all of them and then, so I have a new Z here and then use the forward transformation to generate the corresponding X. This is what happened. You know, this is the Z1, let's tell. This is the Z1, Z3, Z2, Z4. Again, you see exactly the same images. You see, this is Z1, Z2, Z3, Z4. They are exactly the same. What happened for the others? For example, for this image, this is the corresponding Z based on this formulation. I calculate that Z and then pass the Z through the forward transformation and see what happened in the resulting observed world. You see that here it is more understandable images than the case that you simply interpolate the images, the observed images. Assume that instead of interpolating the latent, I interpolate both images themselves. So I have something weird here. But when I interpolate the latent space, it means that something more understandable is generated. And this is the fact that the model find, let's say, a manifold. This is a higher level description of these models. It is not important to understand it very well now, but through your research in this field, you can understand what's happening in the latent space. It means that there is a manifold in the latent space that your model recovers it, and then when you watch on that manifold, every point is a valid point. Every point is corresponding to an image which is understandable. instead of interpolating if you interpolate the images themselves, you see something weird. But if you interpolate the latent space of those images and then come back to the observed space, you see something which is more understandable than interpolating the observed data itself. This is the idea of latent variable interpolation. We have previously talked about the attribute vectors in VAEs. There are also some types of idea in the latent space. This is also another idea in the latent space, and it shows that the model recovers some manifold in the latent space. We can talk about this idea further if you are interested in after the class. Okay, this is also the same idea for faces. You see, if I interpolate, for example, in this point, if I interpolate these 4 images, I have something really meaningless here. You can check it. For example, based on the formulation we have here, interpolate the images themselves and see what you have here. But what happened in this image, instead of interpolating the data, I interpolate the latent and then pass the resulting Z from the forward transformation. And the resulting image is this image. And as you can see, it is a valid image. It means that in the latent space, everything is a manifold which is recovered, and you can walk through that manifold so that every point generates a valid image. And we see that it is not perfect, but it is much more better than interpolating the data itself. And also we see that here you have some attributes of both nearest images. For example, in this image, this image is really similar to both this one and this one, and it means that it is interpolating the features in the latent space. Understandable? Okay. This is another example for the data set of bedroom, and you can see again similar happening we have here. It means that the interpolating the latent is more understandable than interpolating the data itself. This is for church images. Yes?
So on that grid, which squares are from the image itself and which ones are from?
Yeah, the ones with the red rectangle, with the red sign, these 4 are from your data set, and all other images are generated. It means that they are interpolated first, then the resulting Z is passed through a forward transformation, and you have the image here. How it is interpolated using this formulation? You know, these 4 positions are from the data set. Okay, in all of them you can check that these 4 positions are signed by a red line. Okay, all other blank boxes here are interpolated using this formulation. How? For example, I want to focus on this point. Okay, for this point, we know that phi is pi over 4 phi is pi over 4 and phi prime is 0. Okay, put them here. You have the Z corresponding to these images. So if you put them here, you have a new Z. Yes? You pass that new Z through the forward transformation f of theta. So you have new X. What happened? I put that X here. These are the data set. We know that everything is happening in the latent, in the Z. What here is in the observed space. It means that this is the resulting X. Clear?
So all of them somehow used the actual image from the data set?
No. Just these 4 images are from the data set.
But the other ones are interpolated.
Yeah, the other ones are, for example, in this point, I have the Z corresponding to this image using the inverse transformation. Okay? You know, I select 4 images from the data set, x1, x2, x3, and x4. I have a trained model. So using the g theta transformation, I can generate the z corresponding to each of them. Do you agree? So I have these 4. Then I put it in this grid and start filling the blank space. How? For example, for this space, I fill it as this. Z equals the cosine of phi p over 4 times sine of 0, because the other axis is 0. Okay? Cosine of 0 times z1 plus sine of 0 times z2 plus sine of p over 4 times cosine of 0 times z3 plus sine of 0 times z4. We know that sine of 0 is 0, so these two are cancelled. So the first z is really simple because these two are also 1. The first one is, this is also sqrt of 2 over 2. This is also sqrt of 2 over 2, if I remember correctly. So the z here is this value times z1, this value times z3. So I have a new z here. And for all of them, I can fill. Okay? So I have a complete grid of z. Also, I have a forward transformation f of theta. I pass all of them through f of theta. What happened? The result are these grids. These are the results. But I know that these 4 are still the dataset image because f of 3 is exactly the inverse of g of theta, and these are generated using g of theta. So these 4 are exactly the same as before, but all of them, all other parts are generated. Okay? Yes?
Can you go back to one slide? Why did they use that type of interpretation?
Yeah, that's the idea of the authors, you know. Maybe linear interpolation is not working very well.
Oh yeah, I was thinking like p times g1 plus 1 minus p times g2, right? That's a linear interpolation.
Yeah.
So, I mean, is this some kind of Fourier transform? Because I see cosine sines.
Yeah. You know, this is maybe they check different types of interpolation methods, and they found that this method works very well in terms of generating samples. Maybe yeah, because you have some types of interpolation, you can easily linearly, because it is not linear interpolation, you can easily linearly interpolate the data, and maybe in that case you have not very understandable images. Yeah, but here it means that by these types of interpolation, everything is working in the latent space. But we know that to design an interpolation that works in the observed data space is very hard. For example, is there any interpolation that I can interpolate 2 images pixel by pixel such that the result is understandable image? It is very hard. But here you can easily design one of the well-known interpolations and then interpolate the data. Yeah. Any question? Okay. These are, all of them are generated using the same procedure. Okay, let's talk about another interesting flow model, which is also related to our previously models, autoregressive models, and they are really nice formulation for the inverse transformation method. We want to talk about masked autoregressive flows. What happened in masked autoregressive model flows? You just know the forward and the reverse transformation. The forward transformation is as this formulation. For each element in your observed data, you multiply the corresponding element in the inverse data using an exponent which is a function of your previous observed data. This is the idea of autoregressive models. Why? Because to generate, previously we see that to generate a distribution for xi, we use the information of x less than I. Here you use the information of x less than I to generate the transformation. Okay? So let's talk about the index. For the index number 1, what happened? x1 equals z1 times exponent of alpha 1. Excuse me, what is alpha 1? Alpha 1 is a network. Alpha I is a neural network. And mu I is also a neural network. They are neural networks parameterized using the parameters of your transformation. It means that if you give them their input, they generate one scalar. So pay attention that alpha I is from R of the dimension I minus 1 to R. It means that for the if I use 1, for example, alpha 1 is a function from R0, it means that it has no input into the scalar. And also mu1 is, this shows that no input. It is similar to the case that when we want to have the distribution over the first element in an autoregressive models, you cannot condition on anything. Here again, to generate the transformation for the first element in X, you cannot use the previous ones because there is no previous one. You are at the first element. So it is easily the z1 times the exponent of n scalar plus another scalar value. So this is the first one. What happened in the second one? In the second one, to generate x2, you have z2 times the exponent of alpha 2. Alpha 2 is a new neural network, different from alpha 1, where the input is x less than 2. Input x less than 2 has one element. So x less than 2, remember that x less than I equals this vector. So it is in Ri minus 1. Okay? So, are we eligible to use x less than 2 here to generate the transformation? Yes, because previously you have generated x less than 2 in the previous part. So you are eligible to use it as the input to your neural network. Okay? What happened? I multiply z2 by this scalar. Again, what happened for alpha 2? These are a specification for alpha 1. What happened for alpha 2? Alpha 2 is from the dimension 2 minus 1, which is equal to 1, to the scalar, to one-dimensional scale. Space. And also mu2 is also of the dimension 2 minus 1, which is equal again to 1, to R. So these two neural networks generate two scalars for us. The first scalar pass through an exponent and rescale your z, and the second one is also some types of offset to the resulting value. And this procedure here, because x less than 2 is just one element, it means that x1, we can replace this with alpha 2 of x1. It means that a neural network where its input is just the first element and output is just another scalar. And mu2 is also a neural network where its input is just one element, which is the previous one. Why can we use them? Because they are previously generated. It means that x1 is previously generated, so you can use it in your transformation. We continue this procedure until we generate all elements of the observed space. We will see another visualization of this procedure in the next slide. Okay, alpha and mu can be any neural network architecture with single output. It means that both of them are architectures with vector input, and the output is just a single number. Why? Because it wants to rescale the corresponding element in the base space and add an offset to it. So just you need two scales, two scalar values, two numbers, real numbers. And how the inverse transformation, is easily, first, I think that the next slide can show it better. But you will subtract the mu added and then divide it by the scale you add. But now pay attention to this image. What happened? Here, we want to focus on both forward and inverse one by one. For the first element, what happened? I have two parameters of my model, the alpha1 and mu1. First, alpha1 passed through an exponent, and then z1 is multiplied by the result, and mu1 is added, and it generates x1. So, the first element is generated using just the first element in the base space. How we can inverse this procedure? You have access to alpha 1 and mu 1. So again, you first subtract the x with mu 1. You inverse this operation here, and then divide it by the exponent of alpha 1. So you have z1 here. For the first element, I think everything is clear, yes? Now, pay attention to the second element. The first element is generated, okay? So you can use it. I use the first element as the input to these two neural networks, alpha 2 and mu 2. Both of them input x1 and generate one scalar for us. Then I just omit this connection to make this figure simple. But pay attention that these are the result of x1 input the neural network. So then what happened? I use the resulting values to first scale z2 using this line, and also add an offset to the to z2 to the result and generate x2. So this is the forward transformation for the second element, and we know that this forward transformation is a function of the first element we previously generated. And how we can do the inverse? The inverse, again, you copy these two here and inverse each of the operations. First, you subtract mu2 of x less than 2 here, and then you divide it by the alpha 2 of x less than 2 here. So you have z2. Clear? So we continue this procedure for the arbitrary d elements. For the arbitrary d element, you previously generated, this is x2, this is not x1, this is x2. You previously generated x with the index less than d. We see before. So what happened? First, you input the resulting d-1 dimensional vector in these two neural networks. These neural networks accept the x less than d here and output one scalar value. Also, these neural networks accept x less than d here and output a real value here. So then you rescale the d element using this value and then offset, generate the xd. How do you inverse it? You exactly copy these two here and then use the inverse transformations. Oh, sorry, I made a mistake here. This should be here and this should be here. I made a mistake. This is correct, this procedure. Here also, first I should minus this mu d here and then divide this value here to generate z. So this is not correct. I will update it in your canvas. So everything I think is clear. You can generate the z. You can generate x using z, and then how to generate z using x. And the procedure is invertible. Clear? Okay. But the important part, what is the Jacobian? Because we need the Jacobian to normalize it. Okay. The Jacobian for the forward transformation of the coupling, the coupling layer now. The mask autoregressive flow, this layer. This is not a coupling layer. The logarithm of the determinant, the absolute value of the determinant of the Jacobian is, as you can see here. And we know that because the importance of the autoregressive property is here, that the resulting Jacobian is still lower triangular. Why? Because each element cannot use the future elements. What does it mean? X, for example, x1 cannot use the z2 till z2 till the end. x2 cannot use the z with higher index than 2. xd cannot use z with higher index than d. This results in a Jacobian where it is lower triangular and makes everything simple. Why? Because you can easily calculate the determinant using the multiplication of the diagonal elements. So the autoregressive property plays an important role here to simplify the determinants. Okay, and what is the diagonal elements that you should multiply them together to generate the determinant? We know that the first element is multiplied by the exponent of alpha 1 of x less than 1. It's better that to write it less than 1 here, not 1 to 0, because it is aligned with our notation in the autoregressive property. I will update all of them and write here x less than 1. It is better notation. So we have on the diagonal elements are exponent of alpha d of x less than d in the general case. So you have this to some extent simple formulation for the determinants, and also we know that the exponents are always positive, so you can omit the absolute value, and then the logarithm and the exponent are the inverse transformation, so they cancel each other. You have this simple formulation for the logarithm of the absolute value of the determinant of the Jacobian. It is clear? So we just add this term to the loss function in the training, and we know that this is, you have several neural networks, alpha 1, alpha 2, alpha 3 until alpha d, and you should minimize, because this is the Jacobian of the f in the you should minimize them to maximize the likelihood. Okay. Any question? So the mask, the transformation is not volume preserving, similar to real MVP, and we know because you have a scaling on the diagonal, on the main diagonal, and it means that the scale is changing. So let's think of again the sampling and generation. The sampling and density estimation for mass autoregressive is really similar to the previous ones, but we want to pay attention to one important point about these networks. First, assume that I want to sample from a mass autoregressive flow model. What happened? Assume that the latent, the base distribution is normal, is a standard normal distribution. What happened? First, I calculate x1. How? In the sampling, we assume that you have a trained model, so you can easily easily have access to alpha 1 and mu 1. You take the first element of the generated vector and then multiply it by the exponent of alpha 1 and then add the mu 1, and you have your first element in your observed data. When you have this first element, you can calculate mu2 and alpha2. Why? Because mu2 and alpha2 accept as input this x1 and generate the resulting scaling and bias terms. So I use this x1 here to generate alpha2 and this again the x1 here to generate mu2. When I have the access to alpha2 and mu2, I can easily generate x2. Why? Because x2 is the rescaling of z2 using the exponent of alpha2. Alpha2 is here, I put it here and generate this and calculate this multiplication and then add mu2 to the result. So I have the second element of my generated sample. Again, if I have access to both x1 and x2, I can calculate mu3 and alpha3. This is alpha3. I can calculate mu3 and alpha3. Both of them can be used to generate x3. The x3 is z3 times the exponent of alpha3 plus mu3. And these two, alpha3 and mu3, are calculated previously. And you can continue this procedure until you can calculate xd. So, what do you think? What is the problem with this type of generation? What was the, yes?
It's got to be parallelized.
Yeah, exactly. It cannot be parallelized. You should first calculate x1, then input x1 to these two neural networks to generate mu2 and alpha2, and then use them to generate x2. Without generating mu2 and alpha2, you cannot generate x2. Then again, to generate x3, first you should calculate these two scalars using the previous data generated. So the procedure is sequential. And the problem is that you have sequential sampling in MAF as we expect from the autoregressive nature. Again, remember the case of ChatGPT, how it can generate samples one by one, token by token. This is again the problem here. We have exactly the same problem, that the generation is one by one. Okay? But the likelihood calculation is in parallel. When we need likelihood calculation, why do we need calculation? For training. For training, we need likelihood calculation. And if the likelihood calculation is parallel, it means that training can be fast. But if the likelihood calculation is sequential, it means that the training is also very slow. So why the likelihood calculation is in parallel? Assume that in likelihood calculation, instead of having access to z, you have access to x. And you want to know what is the probability that your model assigned to this x. So instead of z, you have x, but because you have access to the complete x at once, you can easily calculate mu1, mu2, mu_d. Because mu1 is a function of x1. mu1 is a function of nothing, mu2 is a function of x1, mu3 is a function of x1 and x2 until the end. So I can in parallel calculate each element of both of these two vectors, and then by the inverse transformation, this is exactly the inverse transformation, but pay attention that all of the operations are element-wise. It means that this exponential is element-wise, the division is element-wise. So first, I have x, I calculate these two vectors in parallel, then use this transformation to have z. When I have z, I can calculate p of z, but pay attention that this is just p of z. You have a normalization factor also here that also is a function of this vector. That function is, this is the function that is the normalization factor. This normalization factor can also be calculated easily using this vector. So you can easily calculate the probability of a data X. The likelihood calculation and thus learning which needs transformation, Jacobian is in parallel for MAF. So the likelihood calculation is fast in contrast to the generation. Any question? Okay. Oh, okay. I think we can talk about the inverse autoregressive follows in the next session. The inverse autoregressive follows is an idea to reverse this procedure. It means that the generation is fast, but the likelihood calculation is sequential and slow. And we will talk about how you can update your transformation such that the generation is fast, but the training is slow, or the likelihood calculation is slow. This is in the inverse direction of the MAF. Any question? Okay, thank you very much. Have a great day.